by more than half of the rules. So if I take the first two positions, then A is still 33 votes, B in 49, C in 33, and D 16, 19, 37, and well, this still doesn't work. And E doesn't work. So we have to go to the, we have to add one more iteration. And so then we take A, B, C. So we take the first three. So A still doesn't work. B, 49, yeah, B that works. And C also. And D, no, and E no. So we have B and C, and then the tie-breaking, it's not the tie-breaking. Then to compare B and C, we take the one who appears most often in the first three positions. Okay. So for B, it's 49, 52, 60, and 82, and C it's 49, 52, 60. 7, yeah, this one. Okay, so the winner would be C. Okay, this rule is called buckling. So this is a rule that exists. Okay, but there are quite many others, and we'll see a few others. But before, okay, so we're going to, most of the rules that we're going to define are defined from rankings, but still, I mean, there might be also, I mean, we may sometimes define the rules that are not based on rankings. So I'm going to spend 5 minutes, but no more than 5 minutes, on defining rules that are based on something else than rankings. These are not because of the difficulty of eliciting numerical preferences. These are not seen as the best methods, but sometimes it works. In some contexts it works. Okay? So the first way of doing is so using numerical preferences, so we can have a profile consisting of utility functions, U1, U2, UN. Okay? And so for instance in TripAdvisor the numbers are between 1 and 10. Is that right? Or 1 and 5? 1 and 10. 1 and 10. And but we can also use a qualitative scale, as we mentioned. And then we have an aggregation function. And so we aggregate the scores for each candidate, and then we output I mean the winner is the candidate with the highest score. Then there are several ways of aggregating the score. We can take the sum. Okay. In TripAdvisor, this is what they do. They take the average, but maximizing the average and maximizing the sum is the same. But we can take the minimum, which is if we want to be fair. Suppose that we have a small number of agents, and we want to find a common language, for instance, and everybody would rank the language according to its abilities to speak the language. So we want to find a rule that maximizes the utility of the worst of the agents, of the least happy of the agents. So in that case, we would use mean, or we would call the variant of mean called leximean, where in case of tie, then we care about the second worst agent and so on. Also, sometimes we can take the median, which has a name. This is called majority judgment. And in this case, Arrow's theorem does not apply. But there are still other aggregation rules. For instance, I don't know. Does anyone know how scores are aggregated for the Olympic Games for sports where juries give marks like ice skating and maybe is dancing no, that is gymnastics. Yeah. I'm not a fan of the Olympic Games. Okay, ice skating definitely. Yeah, you have a jury that give marks to the players. And does anyone know how the scores are aggregated? They don't take the sum, not exactly.
I think they get rid of the top and the bottom.
Exactly, they get rid of the top and the bottom and they take the average of the others.
Yeah.
So this is called the Olympic average. But there are still other ways of doing it. Okay, now let's move to a different assumption. Sometimes we want to be as simple as possible, and then we can ask voters to specify dichotomous preferences. It means that they only have to say for each alternative whether they like it or they don't. Okay? Yes, no. And of course, as you expect, you are going to elect the candidate that maximizes the number of yes. This is called approval voting. So for instance, if we have here 5 candidates and 5 voters, and the votes, so voter A, voter 1 approves A and C, voter 2 approves B, C, and D, the third one approves no one, the fourth approves 5, and the last one approves D. Then the winner will be, the co-winners will be C and D, because they maximize the number of approvals. And again, our theorem does not apply. Of course, I mean, this is so as opposed to numerical preferences that are difficult to elicit because many voters are reluctant to specify numbers. I mean, this is very easy to elicit. It's very easy for voters to say yes, no. But of course, I mean, you lose expressivity. And sometimes it's much better to allow voters to specify rankings rather than just yes, no. But still, I mean, sometimes it's good to use simple methods. I'm going to skip this. Okay. So the conclusion about this discussion about whether we should allow rankings or subsets or numbers, well, dichotomous preferences, so specifying subsets, this is simple, but this is maybe too weak. The expressivity is too weak. You cannot express intensities of preference. Numerical preferences, it is very rich, but we have 2 main problems. So difficulty of elicitation, I've talked about this already many times. And the second one is interpersonal comparison of preference. Because when you use numbers, I mean, these numbers, it's not guaranteed that the same number means the same thing to 2 different agents. I mean, if you give a 7 to a restaurant supervisor, I mean, does my 7 correspond to your 7? There's absolutely no reason why it should mean the same thing. So this is called the interpersonal comparison of preference, which usually does not hold except if there is a neutral measure such as money. If money is involved, then of course, I mean, to some extent we can assume that 10 euro is the same for all of us. It's not even true, but at least, I mean, there are arguments that that could be true in some context. And ordinal preferences, which is the traditional, the most common way of defining voting rules, then it's expressive. We don't have these problems of interpersonal comparison of preference, but of course, I mean, we have our theorem. So but actually, our theorem is not the end of the world. I mean, we can still define many ways of aggregating preferences, which will violate the IIA axiom. Okay, so now let's move to voting rules. So I'm going to define very many voting rules. Maybe this is the most important part of the course, and I hope that in your future life, I don't know what you will do in your future life, but I hope you will have to organize very many elections, kind of elections, such as, I mean, some of you will work in universities, and you will have to make decisions about electing the department chair and the committee, the institute committee. You will have to assign maybe offices to people. You will have to select students for courses, and we have to hire new people. And so I want you to remember that you should try to use a good voting rule and not a stupid voting rule. Okay, so this is not. If I were able to know now that at least one of you will benefit from this course by using it in real life and making real decisions in a few years, I would be happy. So, positional scoring rules. So actually we have already informally defined them 5 minutes ago when we discussed about inventing voting rules, and you got this several of you got this very intuitive idea to associate points with ranks, and this is called positional scoring rules. So we do that. We associate to each rank we associate a score. So S1 is the score for rank 1 for the top alternative of both. S2 is the score for rank 2, and of course the score should be non-increasing. And then we take the sum of the scores and we maximize this sum of the scores. And so plurality, as we said already, corresponds to 1 for the top and 0 for everything else. That was your suggestion. And Borda, corresponds to that. Yeah, so usually we say a minus 1 and minus 2 to 0. It would be the same, if, of course, if we start with m. It doesn't change anything. Veto corresponds to 1 for all ranks except the last one, and then 0 for the last one. So informally, what does it do, veto? It maximizes the number of voters who do not rank a candidate last. Okay. You get a point, a candidate gets a point every time a voter does not rank him last. You see? He gets 0 point if it's ranked last by a voter, and 1 point in all other cases. It means that the veto winner maximizes the number of voters for which it is not the worst candidate. Is that clear? Okay. Also another family of scoring rules is K approval. So K approval actually is a generalization of those two. You give a point to positions 1 to K, and then it falls to 0. So you would select the winner would be the candidate who is ranked in the first K positions by the highest number of voters. Okay? And of course, if K equals 1, then we get again plurality, and if K equals m minus 1, we get V. Questions? Yes? No? Yes? No? Example? So this is again our profile with 100 voters. So plurality, we've seen many times already that the winner is A. He gets 33 points. Borda, so I'm not going to do the calculation. You can check the calculations if you like, and the winner will be B. And that's, I said when I showed this profile, someone, was that you, suggested that it should be B? Yeah. And I said, yeah, there is a good one. Okay, you, okay. That it should be B. And I say, yeah, there is a good reason to choose B. Actually, I believe that border is the best rule. I'm not, but some people disagree. But I mean, I'm very much in favor of border, so probably I would elect B. Then if we choose veto, then there will be 3 co-winners, and there will be a tie between B, C, and D. Because only A and E are ranked last. And if we take C approval, 3 approval, then the winner will be C. You can check for that. And now let's discuss some important properties of voting rules. So anonymity and neutrality, we've already talked about that. Anonymity is when all voters have the same weight, the same importance. And neutrality is when all candidates play the same role. Condorcet consistency, you've seen that already. The rule is Condorcet consistent. If every time there is a Condorcet winner, then this candidate should be the winner. Parity efficiency, again, we've seen that. I mean, if every voter should prefer X to Y, okay, so this is the version of parity efficiency for voting rules. We've seen that for aggregation functions. So for voting rules, if every voter prefers X to Y, then the winner cannot be Y, which is quite important. Monotonicity is the property that says that if the winner is X, okay, so take the profile where the winner is X, and then take one of the votes and move X up in the vote, then of course it should remain a winner, right? Okay, if this property is satisfied, we say that the rule is monotonic. We'll see later rules that are not monotonic, which is intuitively very shocking. Participation is the property that if you have a number of voters who already expressed preferences and the winner is X, and then you have a new voter who hesitates whether to vote or not. If you have the property that when this voter decides to come and vote, then the new winner is either the same as before, or a new winner that this voter prefers to the old winner, then the rule satisfies participation. It means that a voter has always an interest in voting. Okay? It cannot harm the voter to vote. Reinforcement is the property that says that if we have two sets of voters, like think of two districts, for instance. Say, for instance, we have, suppose that we have elections in Crete, and we have like Western Crete, Chania, and Central Crete, and Heraklion. And we have an election in these two parts of Crete. And suppose that the winner in the Western, in Chania, is A, and the winner in Heraklion is A as well. Then if you take the whole of Crete, the winner should still be A, right? If this is satisfied, then we say that the rule satisfies the reinforcement. Some rules do not satisfy reinforcement. Clone proofness is the property that if you take a candidate and you make it, you clone it into two different candidates or more, such that all voters will rank these candidates contiguously. Okay, suppose that okay, we make an election among you. You are the candidates. What's your name?
Sergio.
Sergio. Okay. So then we clone Sergio. So that now there are Sergio 1 and Sergio 2. Okay. And so you have preferences. So some of you like Sergio a lot. They rank him at the top. Some of you don't like him at all. They rank him at the bottom. Some rank in the middle. But when there are two clones of Sergio, you will always, so those who rank Sergio in the top, now they will rank either Sergio 1 or Sergio 2 on the top, and then the other one. Those who rank him on the bottom, they would still rank the two Sergios in the bottom in any order, and so on. Okay. This is and if the rule is clone proof, then the winner should be either the same winner as before, or a clone of the old winner. Okay, so if Sergio was the winner, then the new winner would be either Sergio 1 or Sergio 2. Okay? One question, to see if you got it. Take these positional scoring rules, such as plurality and Borda and veto and K approval, and tell me among those properties, which are those that are satisfied by these rules. I can help you by saying that these either, okay, for each of these properties, either all positional scoring rules satisfy it, or none of them satisfy it. So the answer is always yes or no. It's never sometimes. Okay? Well, anonymity and neutrality, that's obvious. Okay? What about monotonicity? Remember, positional scoring rules are those rules defined by scores. We have a vector of scores. For each rank, we have a different score. And ranks, of course, are not non-increasing. Then Suppose we have the other winner and you move this winner up in one of the votes. Will it remain the winner? Who thinks that it is a yes? Yeah. Who thinks it is a no? Okay.
Can you explain again what we're going to do exactly? Can you explain again what we'll do exactly with the winner?
Okay. Take one of the votes. Take one of them. So suppose we take border. Okay, the winner is B. Okay? Take one of the votes, maybe one of these votes here, and move B before A. To move it, well, will B remain the winner? Yes, the answer is yes. Okay. And this will hold also for other scoring rules, and they satisfy monotonicity. This is not really, it looks like it's easy to satisfy monotonicity, but in fact it is not. We will see many rules that do not satisfy monotonicity. What about participation? Suppose we use border. I mean, suppose you are a voter. I mean, would you? I mean, before voting, I mean, would you think a little bit whether it can harm you to vote? Again, the answer is no, it cannot. Actually, so participation is satisfied by these rules. You give, I mean, you give more. You vote and you will give more points to the one you like. So if the one you like was already the winner. Okay? I mean, this is not a proof. I mean, this is a little bit more complicated, but it's a bit, what about consistency, reinforcement? So, if the winner in the Western treat is A, and the winner in Eastern treat is A, if we put all candidates together, is the winner still A? Yes, because we maximize the sum of points, and the sum of points is the, so because the sum distributes with the sum, basically, maximizing the sum. If A maximizes the sum in the first set and the second set maximizes the sum in the union of the sets. So that makes many properties that are satisfied. Okay, so in Pareto efficiency, that's obvious. So we have unlimited, neutrality, Pareto monotonicity, participation, and reinforcement. What about the other ones? So we have the remaining two is our Condorcet consistency and clone proofness. What about clone proofness? Take plurality, for instance. Take plurality. Okay, so plurality, the winner was A. Okay, let's clone A. So now we have A1 and A2. What can happen?